All right, welcome everybody. Today we're going to talk about lesson 14B, and we're still talking about those chapter 2 calc connections. And today we're going to talk specifically about the applications of the difference quotient and then tangent lines, a very, very, very important concept in calculus. So first, just to kind of set the scene for you, calculus is a branch of mathematics that studied rates of change of functions. That's kind of the whole point of calculus, is to study how quickly things change over time, and then eventually to see how much you're left with after the change occurs. And again, if you go to take calculus next year, which all of you should be, you're going to learn that these rates of change have a lot of real-world applications. So earlier on in the chapter and in chapter 1, we basically talked about how the slope of a line tells you the rate at which a line rises or falls. We kind of already knew that. If you're talking about a line y equals mx plus b, the slope of the line is the same throughout at every single point. That's kind of the whole idea. That is not the case if you do not have a linear function. So for any quadratic or cubic or quartic, you're going to have different rates of change depending on where you are on the graph. And since we've been talking about quadratics, we're going to go ahead and start with that. So consider this quadratic here, and then consider the 3 points that are highlighted. If I was to find the slope of the line on this curve that goes through this point, all I really would know for sure is that this is going to have a positive slope because it looks like it's having a positive change. If I was to go ahead and find the slope here at x2, y2, again, it would have a positive slope because of the way that the line is drawn. But if you look at the slope of the line going through x1, y1, and compare that to the slope going through the point x2, y2, while they're both positive, you can certainly see that they're not the same. Then if you were to draw a tangent line through the point at the top here, you would see that it kind of levels off. And then let's assume that we were choosing some points on the other side. Well, now you're going to have a negative slope. So again, the rate at which the graph is changing is going to be different at each of the different points on the graph. To determine the rate at which a graph rises or falls at a single point, basically what you're going to do is you're going to find the slope of the tangent line and that point. In simplest terms, the tangent line to the graph of the function at some point x1, y1 is the line that best approximates the slope of the graph at that point. So these are 3 examples of 3 different curves showing you some tangent lines which are approximating the slope. So here, if I was to draw a tangent line to this curve at point P, I would get a positive slope. If I was to draw a tangent line to this curve at point P, I would certainly get a negative slope. And then if I was to draw the tangent line in the third example, I would get a horizontal line, which is, of course, a slope of 0. Just a little note here at the bottom about tangent lines. So again, tangent lines hit the graph exactly once. Just so you're aware, in something like this first graph, if you were to continue this line, you would intersect the graph a second time. That intersection would have a different slope at that point, which is fine. We're only going to deal with this point in question. So one option for trying to find the slope of a graph is just to kind of eyeball it. So suppose that we had just the normal function x squared, and you were trying to approximate the slope at the point 1, 1. Well, you would take some kind of a straight edge, and you would go ahead and draw this tangent line. If you were to choose some points in the nearby area, perhaps you would look at it as going over 1 and up 2. And because a slope is a rise over run, change in y over change in x, that would be a positive 2 over a positive 1. So you could approximate that slope to be 2. This is not a very efficient process, and it gets harder and harder as the values get larger and as the graph itself is less precise. So of course, in math, we want to try to be as efficient as possible. And the way that you'd be as efficient as possible is by using something called the limit process. So again, here's where we're really getting into the calculus. So more important that you listen and ask questions than it is that you write anything down. So let me just go ahead and change back to my pen here. Okay, so a tangent line is a great thing. And again, a tangent line hits a graph at exactly 1 point. Something that happens before you can become a tangent line is you can make a secant line. Hopefully you remember that a secant line hits a graph exactly twice. So again, look over here at the picture. Let's say that we have some random curve here, which is in black, and we're going to choose 2 random values on that curve. So when you choose a point on a curve, you normally choose the point xy Because we're talking about a function, we're going to call that x f of x. Then we want to choose a second point some distance away. To say some distance away, we're going to use the value h. So you're going to go some distance to the right, which means starting at x, going some distance away, you're now going to be at the point x plus h. Then in the same way, you plug x into the function to get f of x. You're going to plug x plus h into the function to get f of x plus h. Now that you have chosen 2 points on the black curve, you would draw the secant line between them, which would be the pink line, and you would go ahead and find that slope. Well, how do you find the slope? You do y2 minus y1 over x2 minus x1. We're going to use this point right here to be my x2, y2. So when I do y2 minus y1, I'm doing f of x plus h minus f of x, y2 minus y1, all over x2 minus x1. If you take a look at this formula, it should look familiar. And then if you look at the denominator, something good happens, which the x's cancel, which means you're just left with f of x plus h minus f of x over h. That is the difference quotient, something that we saw earlier in the year, and we saw again a few days ago. And it turns out that the difference quotient, what that is really telling you is how to find the slope of the secant line for a curve. The way that you abbreviate that is by saying m sec, m for the slope, and sec for secant line. So the slope of the secant line from this point forward is the difference quotient. That's the point. I think earlier in the year, some people were really not sure what the difference quotient did, and here's where it comes into play. So again, if you're being asked for the slope of the secant line, it's going to be the difference quotient. How can we take that secant line and try to get the best possible answer? Because right now, the 2 points that I've chosen, even though they're not too far away, they're not terribly close either. So what I'm going to do is I'm going to go ahead and move those points closer together. If I'm going to move those points closer together, that basically means I want the h to get smaller and smaller and smaller, which means I essentially want it to be 0. So let's consider what would happen if we do that. So look at the graph all the way to the left. That's the same picture as the previous slide. Then in the next graph, slightly closer. In graph number 3, slightly closer. And when they get so close that they're essentially on top of each other, they basically become the same point. And if you have just 1 point instead of 2, that's what turns it into a tangent line. So how did you do that? You made the h approach 0. You've probably heard this word thrown around before, but the reason why you're allowed to do that is because you can take what's called the limit. So big concept in calculus. And again, of all the things you're going to write down today, this is probably the one. If you are trying to find the slope m of a graph at a given point, it's equal to the slope of the following. So again, 2 different things here. If you're, sorry, I kind of mumbled my words there. So if you're looking for the slope of a graph, you're going to go ahead and start by finding the slope of the secant line. If you then want to turn it into a tangent line, you have to take the limit. And the limit means you essentially want to make the the h go to 0, provided that the limit exists. We're only going to do ones where it does. But again, you want to make sure that you take the limit. If you don't take the limit, it's just the secant line. It doesn't become the tangent line until you actually go ahead and take the limit. And again, the whole reason why we're doing this is because of its important applications in calculus. It's so important that one of the topics in calculus is called the tangent line problem, which is essentially this. So now that you've written down these 2 formulas, and again, the difference quotient is the slope of the secant line. It only turns into a tangent line once you take the limit as h goes to 0. Let's go ahead and see what a problem would actually look like. So find the formula for the slope of the graph of the given quadratic. I put the formula down here as a reminder. So to find the formula for the slope of the graph, you're going to go ahead and take the limit of the difference quotient. So in order to do that, you're going to first start by finding the difference quotient. So f of x plus h means the same thing that it always did, which means go to the function. Everywhere there's an x, you're going to put an x plus h. So negative parentheses x plus h squared minus 2 times x plus h plus 8, and that's just f of x plus h. Then this is a subtraction, so do a subtraction. Then you are subtracting the whole function f of x, so make sure you use parentheses. Again, negative x squared minus 2x plus 8. This is all still over h, but I'm going to leave that h out for a minute just so I can go ahead and do the work with more room. So I'm going to have to go ahead and actually start, going to have to start and actually do the work here. So I'm going to start by doing the FOIL. So the FOIL here is going to be, get rid of that. So the FOIL here is going to be negative x times x is x squared. X plus h times x plus h, the outers and the inners would give you xh, and there's 2 of them. So that's 2xh plus h squared minus 2x minus 2h plus 8. Distribute the minus, plus x squared plus 2x and minus 8. So what I did so far, I distributed the minus here. I distributed the minus here. I did this FOIL. Next order of business is I'm going to go ahead and distribute this minus. I'm going to go ahead and move to the next screen just so I have more room. So if I distribute that minus, I'm going to get negative x squared minus 2xh minus h squared minus 2x minus 2h plus 8 plus x squared plus 2x and minus 8. Hopefully you remember from a few lessons ago that this is the place where good things should happen. What do I mean by good things? Everything that doesn't have an h should cancel. So negative x squared with positive x squared, positive 2x with negative 2x, positive 8 with negative 8. I'm essentially left with only things that have h's in them. Then go back and don't forget to put the h back in. Remember, just jumping back to the previous slide for a second. This whole thing is supposed to be over h. I just left it out for a minute because I didn't want to write it every single time. So now take a look at what you have there. It's beautiful. Every single term in the top has an h in it, which means you can go ahead and reduce an h from everybody. So if I do negative 2xh divided by h, that's just going to give me negative 2x. If I do negative h squared divided by h, that's going to give me negative h. And if I do the third calculation, that's going to give me negative 2. So negative 2x minus h minus 2, this is what's known as the slope of the secant line. Again, secant lines are nice, but they're not good enough. How do you change it from a secant line to a tangent line? Well, you're going to take the limit. It's always the limit as h goes to 0, because remember, you're trying to get those points to be closer and closer together. What does it mean to take the limit as h goes to 0? Well, it means you actually put a 0 in for h, which means you're going to be left with the equation negative 2x minus 2. This is your conclusion. This is the formula for the slope of any tangent line. So if you want to find the slope for anywhere on that curve, this is the general formula for the slope of any tangent line to the original quadratic that I gave you. So that's a pretty powerful thing. Sometimes I might just say, find the slope of the tangent line and leave it like that. More than likely, I will ask you to find the specific slope at specific places. So same problem, negative x squared minus 2x plus 8, but now I've gone ahead and given you the picture. So you're going to find the slope of the tangent line at the point 2, 0. Whenever you're asked to do that, the only value that matters is the x value. So the point 2, 0, all we care about is that that's where x equals 2. What are you going to do with that 2? Well, you're going to take the slope of the tangent line you found on the previous slide, and you're going to plug in x equals 2. So negative 2 times 2 minus 2. Negative 4 minus 2 gives you a slope of negative 6. Now I ask you, if you were to sketch in this line at the point 2, 0, does negative 6 seem like a reasonable slope? Well, I think so. It's negative, which is good, and it's pretty steep, so negative 6 seems reasonable. That's kind of the whole point. What about negative 4, 0? And again, if we're going to do this here, the only thing I care about is that x equals negative 4. Don't care about the y value because I don't have a y value in my formula. So negative 2x minus 2, if I plug in negative 4, 8 minus 2 is positive 6. And if I was to go ahead and draw the line in here, I think saying that a score of or a slope of positive 6 seems reasonable. And if you're thinking to yourself, those seem to be symmetric, yeah, that's true. There's a reason for that. And finally, last but not least, what happens if I try to find the slope of the tangent line at the point negative 1, 9? Well, that's at x equals negative 1. And perhaps by looking over at the graph, you can figure out what's going to happen and really what should happen. So negative 2x minus 2, if you plug in x equals negative 1, you're going to get 2 minus 2, which is, of course, 0. That should make sense because look what happens when you draw that tangent line. That tangent line is a horizontal line, which, of course, always has a slope of 0. So what does that kind of tell us? It tells us that the slope of the tangent line equaling 0 means that you have either found a maximum or a minimum. So that's actually one of the biggest, most important conclusions, that not only can you find the slope of the tangent line, but if you specifically find where the slope of the tangent line is equal to 0, then that means you have found the maximum or the minimum. So homework 14 is what you're going to go ahead and do over the weekend. Homework 14 encapsulates not only this lesson, 14b, but also 14a, which of course was the intermediate value theorem and all the different kinds of discontinuities. So thanks very much for tuning in, and we will catch you next time.